I would like to welcome back Preacher Huang. We have been now locked in a global race way faster than NASCAR racing. And it's partly your fault. Jensen's been the preacher that's given us all the power we need, all the energy and some more to have what I think has been the craziest 12 months of my life, certainly for many of you. And we're just getting started. The energy with which you approach every single thing you do, including the class last year. And then every time I've had the chance to hang out with you, you've given so much time to the students, to the founders. Thank you. Should we jump right in?
Yeah, let's go.
All right. We're going to go rapid fire. What is co-design and why is it so important?
I'll answer that in a second.
Yes, please.
But this is a great time to be in computer science. And obviously the reason is because computing is being reinvented for the first time as dramatically as it is for the first time really in about 60 plus years. The computer that we know of, that you all use in our computing model, our mental model of a computer, the architecture of a computer, how you write the program, run the program, how you think about even taking computers to market, what it's used for 64 years, it has been largely the same since the IBM System 360. In fact, my first architecture book for learning about computer architecture was the System 360's manual. And so a lot has changed as we went from PCs to internet and mobile and cloud and all those things. But the fact of the matter is the computing model, the fundamental part of computer science has largely remained the same until now. You know, for the first time, the way you write the software, how you process the neural network versus the software, and what the applications can do has now dramatically changed. Everything is fundamentally different. At the highest level, you know, one simple way to think about it is computing as we knew it before was largely pre-recorded. It's content that we pre-recorded, images, videos, you know, software that we largely pre-recorded. But now everything is generated. And the nice thing about generating everything in real time is that it could be contextually consistent, contextually relevant to what it is that you're dealing with. And of course, it can respond to your intention, not just explicitly to the things that you instruct. And so the computer is fundamentally different in that way. Now, the question is, what does that mean at every single layer of the stack, from how the software is now developed, the methodology of it, how you organize your company to be able to develop software of today, completely changed. And so the methodology, the tools we use, the approach that we think about software coding, completely changed. How we run the software, neural network versus compiled binaries, very, very different. And so what does that mean to the computer system, the network, the storage? What does that mean to the software stack and the cloud services that sit on top of that? And of course, you know, everything about the applications. What did it open up? And somebody just came and said, this piece of software we just opened up called Alpamayo. And I've been working on self-driving cars now for about 13 years. And the days of robo-taxis are going to be literally everywhere. You know, everything that moves will be robotic. And that's an example of an application that we wouldn't consider doing until deep learning and artificial intelligence came along. That was such a big unlock, that, you know, I said, hey, all of these problems that we wanted to solve in the past that we needed computer vision for, really are now fundamentally unlocked. And so it's how you think about every single stage of that. What is a software engineer? How do you organize the company? what is a computer for the age of AI? How do you architect that? All the way to what you can use it for, and therefore, where you would deploy it. All of that has fundamentally changed. And for me, the journey really started about 15 years ago. And, I had the benefit of seeing some early works in the area. And, as all Stanford students do, you break the problem down, you reason about it from first principles, and you come to the conclusion, literally everything has changed. And so here you are, computer scientist students. This is really the first generation of AI becoming useful. And where we a couple of years ago was in the generative part of AI, and as you guys know, generative AI not only made it cool for us to do image generation and text summarization and translation and whatnot, but generative AI also enabled us to think. And so when I saw generative AI, what other people saw was that it was able to generate images, and I surely would appreciated that as well. But the fact that you can generate thoughts in the form of images, but you can generate thoughts, you can also reason with it. And the ability for AI to think after GPT was very, very obvious. Now the question is how would you train, how would you fine tune an AI, to be able to reason step by step by step, and how would you teach it how to do so at fairly large scale in a kind of semi-supervised way? And so those are kind of the engineering problems you had to solve. But the moment you see GPT, you say, aha, thinking is just around the corner. And thinking is generating tokens that you consume internally, and generating tokens that you consume externally would be called tool use. And so the idea that after GPT happened 2 years ago, that we would be at this moment was fairly easy to predict. Now, of course, unbelievable amount of technology was invented, and a lot of amazing people did amazing work, but you could almost see that moment here. And so here we are. You now have agentic systems. And so now the question is what's next? And what happens in a world where a computer is not responsive to what you ask it to do? It's not but on demand. Today's computing is really on-demand computing. The word on demand was actually created in our generation to talk about how you think about using computers. Time sharing computers that you would use on demand became cloud computers. And cloud computing, of course, is on demand. But in your new world of agentic system, the computers are now continuously running. And so what happens in a world where the computers are continuously running? What happens to cloud services? What happened to your personal computer? What happens to, all of these different systems? Now there's a great opportunity again to rethink all of that. And so what is kind of my introduction to everything about computer science has changed, and everything about every field of science has changed because of the things that we've changed. And so this is a good time to go to school.
Okay.
That's it. What was your question?
You know what? I'm just going to turn it over to the kids.
Co-design.
No, let's just go into the students have questions. They've all been asking questions in Discord. They're all voting on each other's questions.
Co-design is really interesting, but co-design is super interesting. And basically co-design said back in the old days, we abstracted computing so that the people who design microprocessors, people who worked on compilers, and people who worked on languages, and so on and so forth. You guys know that. And we actually had different fields. But the problem, and in fact, this happened at Stanford. What's the beauty of RISC? What was the beauty of the work that John Hennessy did? The beauty of it is that you got to think about compilers and microprocessor architectures harmoniously, co-designed, because otherwise you could end up creating a microprocessor that's super, super tight, and everything is maximally optimized. But unfortunately, it's hard to compile. It's difficult. It's not compilable. And so they created a simpler instruction set that exposed simplicity to compilers so that compilers could do a better job generating code. And it turns out a simpler machine co-designed with a compiler creates better performance than two systems that were optimized individually. That's very Stanford. Okay. This is part of your heritage, as all of your, in John Hennessy's, trail of amazing work that's left behind. And so you take that and you think about, well, what happens in the post world of general purpose computing? Why is it that every problem in computer science would be solvable by a general purpose instrument? At some level, you could say, well, if you had a general purpose instrument, you prefer that. However, there are some extreme problems, whether it's computer graphics back in the old days, or molecular dynamics, or quantum chemistry, or, fluid dynamics and large multi-scale, mesoscale multi-physics problems, or deep learning. These problems are so computationally intense. Why would you use a general purpose computer to go do that? And so the big insight is, what if you understood the algorithms, understood the computer systems, understood if you will, the compilers, the frameworks, and understood the architecture of chips, and you were optimizing all of it at the same time. And so the facts, here are the facts. This is what happens when you do it, what I just described. NVIDIA is probably the first computer systems company that's extreme co-design, meaning we literally co-design across all of that, and including CPUs, GPUs, networking, and switches, and and storage. And so the question is, what do you get? Well, Moore's Law back in the old days, you guys all know about that. Moore's Law was about 2x every 18 months, so call it 10x every 5 years. Okay, so 10x every 5 years is 100x every 10 years. And that was in the good old days of Moore's Law. And for all the computer scientists in the room, you know that Moore's Law was underpinned by a concept called Dennard scaling, and Dennard scaling ran out of steam several years ago, probably about a decade ago, in fact. And we kept squeezing it. But over the course of last 10 years, if you just allowed microprocessors to continue to scale, and you just don't touch the software, and you just benefit from the speed up of semiconductors and microprocessor design, at best case, you would have gotten 100x, but probably because Dennard scaling slowed down and Moore's Law largely ended, you probably got something along the lines of 10x over the course of 10 years. Well, in the case of NVIDIA and co-design, we got 1 million x over 10 years. 1 million x. And so somewhere between 100,000x and 1 million x. Okay. So when you're talking about numbers that big, it really doesn't matter. And so 1 million x over 10 years, we were able to get scaling and computation scale so large, so fast, that AI researchers say, why don't we just take all of the internet? Why even worry about what data to go curate and what data to create? Let's just take all of the world's data and just give it to the computer. And that's really the big breakthrough. When you're able to do something so insanely fast, for example, if you were able to travel at the speed of light, where we choose to live doesn't matter. If you were able to go from New York to California in 10 minutes, our freedom, everything about society would change, right? And so if you're able to do computing 1 million times faster, everything about computing changed. And that's really the big breakthrough. Because of co-design, because of the way NVIDIA approached it, we accelerated computing by so far that it created all this infinite abundance opportunity for everybody to think about the future. And so anyways, here we are.
Cool. I have a bunch of follow-up questions, but I'm not going to ask
that. One word led to that.
GPT-10.
That's what it's like to work at NVIDIA. You give me one word and you get ranted at for about half an hour. Because I got too much to share with you.
The question is, how should education evolve in response to the industry as it's changing?
Yeah, and that's a really excellent question. And I think the answer clearly is AI should be part of your curriculum, not just in learning about AI, but using AI for the curriculum. The problem with textbooks, as you know, it takes an enormous amount of effort to do. And when I was taking classes at Stanford, Professor Hennessy was still writing his textbook. It was all handwritten out. And each week